Apologies. All right, let's try it again. Good evening. Welcome to Code Connector. This is the fourth Tuesday meetup. For those who are joining for the first time, who may have seen this posted on TikTok or Twitter, you may be wondering what the heck is a Code Connector. Real simple. We're a nonprofit tech meetup group, like-minded individuals. We like coding together, sharing experiences. We like to help people make their transitions into tech and then thrive once they get here. We offer nothing to sell. There's no courses. There's nothing to sell whatsoever. Everything is free. And when we direct people to resources, we like directing them to documentation, free resources, and low-cost resources. We do have a particular place in our heart for people coming from underrepresented minorities of any and all types, but everyone is welcome. And at this point, we have about 1,000 people on our Slack channel, which I'm going to drop a link to our Slack channel down in the bottom in the chat in just a minute. Love to have all of you there interacting with us and hanging out with us. For the most part, we are very much an online group, so everything we do is in the form of meetups. Once a month, we have a data structure algorithm challenge. Once a month, we have a UX UI meetup. We have one where we call it Code and Share. Just bring whatever project you're working on, share it with others. And then, of course, on the fourth Tuesday, we have like our big feature speaker. And we've had some really cool ones throughout the months and years. So tonight is no different. The person I'm going to introduce, very special character for me. I remember probably, God, was it a year and a half ago? I don't know. I posted a video because I had a little dumb AR thing on my phone. Like, wow, it would be really cool to code in AR. And I put that on TikTok. And like, people were like, yeah, it's cool. Yeah, it's cool. Yeah, it's cool. And one particular person said, no, it's blank. And it was a very uncool word. Like, you don't even know, like it can be very horrendous. I'm like, okay, interesting take, whatever. Time passes and I'm studying. I think a week or two later, I'm studying. And just for a funny thing, I come across like a lot of really complex mathematical formulas, complex to me at least. So I posted that on TikTok. Hey, when you want to get deeper into studying code, and I just like showed all the math formulas, like kind of to give that feeling like when a movie scene, they wanted to make it look real tech and scientific. It's a bunch of graphs and formulas, and everybody's like, oh no, I would be out. Like, nope, miss me with that. Then this one person's like, I think I'll stitch the video. He stitched the video and completely explained it, like just taking a walk down the park. I'm like, okay, this guy is a little special. And that was none other than Joseph Whittington, who's going to be giving our talk tonight. I was working on like his bio or whatever in conjunction with him. Is he more a computer graphics programmer? But he's kind of dope with the art rendering in digital. Is he more a VR guy, an AR guy, a gaming dev, but not, I don't know. I don't know how many titles he holds, but it's going to be an awesome talk. I'm very glad to have he's joining us tonight. You can see him on TikTok at _Whittington. And if he wants you to see him anywhere else, I'm sure he'll show those socials. So turn on your mics for a second. We're going to give him a round of applause and we turn it right back off so the camera focuses on him. Everyone, please welcome Joseph Whittington. Whit, it's all you. All right, mic's back off, guys. Thanks.
All right, what's up, everyone? All right, so like you said, I'm Whittington. I'm a computer graphics programmer at a small VR studio. And I'm here to show you guys how to render some stuff in 3D on the web. All right, how do I share my screen? All right, that looks fine. All right, so this is what we're gonna be building right here. It's just a basic landing page. There's some animation that happens here. It's not too crazy, but 3D stuff is a little bit more involved than you'd expect. So there is a little bit of work that has to go in. But it's okay because I have slides. All right, so this is going to be a quick introduction to 3D rendering on the web with Three.js. All right, so why would you want to do this? All right, so the big sell for this is that you can use this for product rendering, or you could use it for like landing pages for cool effects. I've seen people have like their portfolio website where it's a full like Three.js game, and as you scroll, it's like traversing through the background, either a car is driving or a character is running around, and it's revealing scenes that give details about expertise and stuff like that. I think the biggest thing though is for project rendering and for previewing 3D models. All right, so what's needed for Three.js? There are some like prerequisites that you need if you're going to be working with Three.js. You're going to need a decent understanding of 3D space. So when you work in 3D, you're gonna need like a solid understanding of how things are positioned in 3D space, and that spatial awareness is like really important because unlike all the other 3D apps that you're going to be using, you're going to be doing a lot of this with just code, and you're not going to be able to preview it until after you've written some code. So you need to have like a mental model of where everything is going to be positioned and what it's going to look like as you're writing the code, and then you'll be able to like debug afterwards uh, when you actually see it render, or if you don't see something render, and that can be a big hindrance. So that's an important thing. You need to have that 3D spatial awareness, and it'll come with time. You're gonna need some basic linear algebra. Nothing too crazy. Just you need to, at a bare minimum, have a good understanding of vector math and vector transformations, affine transformations with 4x4 matrix. So basic stuff like God damn it, like a transpose. You're gonna be able to move stuff, rotation, scaling, shearing, stuff like that. You're also going to need an understanding of the 3D art pipeline. So this is important because with 3JS, you're going to have to be loading 3D content. And if you don't understand the 3D art pipeline, you're not going to understand what's happening when things break. You're not going to understand what files do what, how the different things work. You need a pretty solid understanding of like what each file is, what kind of data it contains, and how you can leverage that. And you need an understanding of material systems and lighting and shading models. Um, this isn't like super detailed unless you're trying to make something that looks really nice. But at a bare minimum, you need to understand like what a basic material is and how to use like simple lights and maybe write a quick shader. All of these things you don't need to know in like a great amount of detail. You just need to know enough to get around. All right. So on the front end, what you're going to need is basic understanding of JavaScript. You're going to need to know some CSS and CSS animations. Um, you're probably going to have to be pretty solid at CSS, if I'm being honest. If you're struggling with CSS, 3D is probably not the best thing for you to be doing. You need that strong foundation because it's going to rely on you not struggling at all with the front end stuff. You're going to need some simple JavaScript animation techniques. You're going to need some programming knowledge. You might need to leverage some advanced data structures here and there. And you're going to need to be able to Google stuff. So how we're going to accomplish this effect, you basically have to do two things. You have to set up 3JS. And then once you have 3JS set up inside of 3JS, we're going to be using a displacement map, a bump map, and a diffuse map. So on the 3JS side, the three things that we need to initialize for any 3JS application is the scene, the camera, and the renderer. And then you're going to have to initialize the lighting. The lighting is optional depending on what your shading model is going to be like. Not all of the materials interact with lighting, but we're using the standard PBR renderer, which does rely on lighting because it's physically based. It's simulating light in the real world using a series of textures. So we do need the lighting for that. And we're going to have to initialize our 3D models and our textures for those models. We're going to have to configure some animation triggers and some timers to get the animations that were on the page. We're going to have to animate some motion for the rotation. And then we're going to have to add some displacement scaling animation for that effect where you see the displacement animated. And on the displacement side, so we're going to need the displacement map because that's what moves the vertices. So the mountain, that's not an actual model. What we're using is a plane, and we're subdividing the plane with a bunch of vertices, and we're using the displacement map to displace the vertices to create the terrain using a texture. I'm going to explain all of this in more detail. This is just like a general overview. I realize I'm going kind of fast. All right, and the bump map is going to change the way each pixel interacts with light to add the bumpiness to it and give the texture. So it's called the bump map. And the diffuse texture is just what gives it the color, the base color. All right, so you need to understand a little bit about rendering. So the rest of this is going to be me explaining the basics of rendering so that you guys know what's going on. And then I'm going to show the code afterwards. All right, so these are the basic things you need to understand about rendering to be able to function within 3GS. So you need to understand how the 3D elements and the meshes work. You need understanding of the materials and the rendering and how the materials go into the rendering. And you need to understand the lighting and the light system and the scene setup for 3GS. And so the 3D elements, the meshes, and the primitives. So when you're working with 3D objects, the 3D objects are made up of triangles, and the triangles are made up of vertices. So I'm going to show a diagram right after this slide, so it'll be a lot easier to visualize. So yeah, these triangles are defined as 3 index positions that point to positions in an array of vertex data. So what you'll do is you'll define a vertex data structure, and then that'll have the information about each vertex. At a bare minimum, you need some you need a vector to store the 3D position data, and you need some UV coordinates to store the texture data. But there's a lot of other things that you can embed in the vertex, and the vertex is the heaviest part of a mesh data structure. And the old way of representing vertex data used to be that you would just store vertices 3 in a row, and then that would form a triangle, but that would create a lot of duplicate data. So we switched to a model where we have an array of vertex data where there's no repeating vertices, and then we have a separate array of just integers that represent indices that point into the vertex array, and then we can reuse those vertices without having to store duplicate data. This wasn't a problem initially, but now that we're getting into 3D models with millions of vertices, we kind of need this. All right, so a primitive is something in 3JS that defines a shape and some properties. So some common primitives that you're going to see in any 3D application are things like circles, planes, which is just like a 2D square that exists in 3D space. You're going to get cubes, torus, cone, and then like a cylinder. I think 3JS has another, they have another primitive called a ring, which is kind of weird. I've never seen that before. And so in 3JS, they separate a mesh from a primitive. So for them, a primitive just defines some properties for a shape, and it usually creates a mesh as well. But you can also create a separate mesh, which uses a primitive to define the data structures necessary for rendering, which is the list of vertices and the indices that create the triangles. All right, so this is an example of one of the meshes. This is the Stanford bunny. This is one of the most famous models in computer graphics. If you get into computer graphics, you're gonna get sick of seeing this. The one on the right is the original mesh, and the one on the left is a subdivided mesh. Back when computer graphics was early and still doing CPU rendering, something on the right would be more common, but now that we have more processing power, something on the left is more common. All right, so the material and the rendering. So when you render, essentially you're just taking a 3D mesh and you're creating the triangles from them, and you project the triangles onto a screen. So there's going to be a diagram after the slide to kind of explain it a little bit, but essentially imagine like your computer screen as like the lens sensor for a camera, and just imagine like another plane the size of your computer screen that scales and gets larger in the distance, and that creates kind of like the camera view. And you essentially just draw something from the center of this screen to the other thing, and then use those lines of intersections to kind of figure out where it's going to be on the screen when you do your 2D projection. And that kind of creates like 2D triangles on your screen that you then have to fill in. And then that's where the material comes in. And the material is running some C code that is a shader that runs on the GPU. And that essentially has a bunch of functions that define the behavior for how it interacts with light and how each pixel gets filled in individually. All right, so when you're using the material system is going to be simulating lighting, either in a stylized fashion or photoreal fashion. but we'll be doing photoreal in the example you saw. That was using, I believe it was using satellite data that was pulled from a satellite. It's very low resolution, so it looks kind of terrible, but if you had high res data, it looked pretty great. All right, and so yeah, right here, like it says on third point, the materials are going to define how pixels covered by an object interact with light. I know this is kind of like going into detail, but honestly, like each of these topics can be explained with like excruciating detail to the point where it's like a whole class by itself. So here's an example of the camera projection. So imagine each of these planes is like a separate like monitor, and then the point that it's like connecting from would be like where the camera is positioned. And basically you draw a ray from the camera position to the tips of the triangle, and the ray, as it intersects with the screen, will form a 2D triangle, and that is how you do the camera projection. So then you take that 2D triangle and you apply the shader to it. And the shader is part of the material. All right, so lighting and lights. All right, so the lighting is defined by the lighting model. There's a bunch of different lighting models that exist. In the early computer graphics, we started with like really simple lighting models where we would shade an entire triangle at once. And then we got a little bit more advanced where we would compute the lighting on each point of the triangle, and then we would blend them together. But now we've gotten so detailed that we provide textures that give additional details for every single part of the triangle. And then we look up those textures on the GPU as we're computing the shader. And then we compute a new value for each pixel. And then we also use some of the blended values from the vertex as an optimization, because those tend to not change as much. So the lighting model that we're going to be using is called PBR, which is physically based rendering, where you use a series of textures that define physical material properties to simulate the way light works in the real world. So some of these are things like the bump map that defines like the bumpiness of a structure. And then you have things like roughness, metallicness, ambient occlusion, which is like a map of like how close something is to something else of varying height, because those things will naturally be darker when they get hit by light. It'll get hit with less light because of the height difference. Stuff like that. And yeah, so that's what we're going to be using. The PBR shader, the PBR material in Three.js is what they consider to be their standard material ever since they upgraded to a PBR system. So that's what we're going to be using. This is the rendering equation. I'm not going to bother showing it. I'm going to share the detail for I'm going to share the slides afterwards. If you want a full breakdown of how the lighting is computed, you can look at this. It's not as bad as it looks. I swear it's not as bad as it looks. Like all of this is like maybe 80 lines of code. All right, so the Three.js scene setup. So when you're doing any 3D application, you're going to have this 3 main phase kind of app breakdown. So you're going to have the initialization, where you set up all of the things that you need to like get your scene up and running and do your first render. And then you're going to have the render loop. This is an infinite loop that basically runs until you quit the application or the application crashes. And then after you close the application or the application crashes, you're going to run the cleanup code. I did not write any cleanup code for my example because I'm lazy, but this is important if you have an app that's going to be stopping. But for something like this, where it's like a website and it's always going to be running, you actually don't need any cleanup code. All right, so yeah, for our initialization, we're going to be setting up the camera, the light, and the renderer. And we're also going to be initializing our models, our materials, and our textures. All right, so I'm going to explain what a displacement map is, because that's what we're using to render the terrain. All right, so these are things that you need to understand about a displacement map: what it is, how it's stored, how it affects meshes, and the tools that are associated with it. All right, so a displacement is just a texture that stores an offset for the vertices of a mesh. It's stored in grayscale, which is important. This is important because textures have 4 channels per pixel. Depending on the texture, some of the older textures only have 3 channels because they don't store an alpha value for transparency. So most of the textures that you're going to use in computer graphics will support an alpha channel. So the 3 channels, RG and B, typically will map to X, Y, and Z on your vector. And the alpha value is usually reserved for either texture packing, which is where you take a texture like this that's grayscale and you put it into the one thing, or use it to store a scaling value. All right, so since this is grayscale, what that means is it's only using one channel. So typically you would texture pack this. So you would take something else that's using 3 channels, and then you would store this in the alpha channel. And then you need to use one less texture, and that's like less data you have to ship across the web. But we're just using it as the one image here to simplify it. All right, so yeah, so it's stored as a floating point number from 0 to 1. But displacement goes both negative and positive. So when you're reading the displacement, you're gonna have to translate from 0 to 1 to negative 0.5 to 0.5. And then you're gonna be using a displacement scaling factor. The displacement scaling factor is basically a number that is gonna be like the maximum. So if something is like going down by 0.5 or going up by 0.5, that'll mean that it's being displaced by the maximum factor. So if you set that to like 100, it's going to be displaced by 100. You're gonna have to multiply by 2 first because it's 0.5. So it'll be like if you want it to be 100, you're gonna have to set it to 200. So that's something you take into account, or you could just double this number. But that has some issues sometimes with the floating point number, because in the shader sometimes they use half precision numbers, and the precision can cause issues with that. So that's something to be aware of. So the associated tools is just like other textures that you're going to be using with it. All right, so so the displacement is used typically with a bump map and a normal map. So the normal map is a texture that defines a 3D vector that UV wraps along a model and redefines where the surface points outward for lighting. So this will make sense when I show you some images afterwards. But essentially what a UV is you take a 3D model and you project it to 2D space, and you cut it up into little pieces and you fit it into a little square. And that square maps to a texture. So when you want to change the texture on a 3D model, you go into that 2D mapped texture and you apply it there. And then it'll essentially be applied to the individual triangles when you're rendering. And that is how you add color and all of the various texture properties to a 3D model. Again, it'll be a lot clearer when you see the imaging. And the bump map is very similar to the normal map, as in it affects the way it presents. So the normal map will mostly affect the smoothness of an object, whereas like the smoothness in terms of like silhouette, whereas the bump map does not affect the silhouette, but it will affect the granular detail. So if you're looking at something like dead on, you won't see much of an effect with the normal map. You'll see more of an effect on the normal map along the edges of an object. But the bump map will show you more detail when you're looking at it head on. You'll see the detail reflected in the texture because it has a significant effect on lighting. All right, so here are some of the images to make the things make more sense. This is an example of a UV map. So this 3D model right here was unwrapped into these things. This is what the face looks like. I know it's can be kind of horrifying seeing this for the first time. So yeah, this is what a 3D face looks like when you UV unwrap it. It gets cut along the back of the head usually. And so now if they want to color this, they just come color in this little part here. And then same for the torso and then the legs. And I assume this is the arms and the hand and the rest of the clothing. So that's what the UV map looks like. This is used for like all of the textures. So this just needs to be generated once, and then the UV coordinates are added to the vertices in the mesh, and then you can use that to figure out where the texture needs to go. This is what the displacement map looks like. It's also called a height map commonly. It was called the height map initially, but now it's being called a displacement map because of the new PBR lighting model. We call it a displacement map. But in other shader models and lighting models, it's going to be called a height map. So you have the texture. So the texture is just going to be like the color. This is the diffuse map. And here you can see the displacement map. It'll have very similar textures to what it would look like if it was actually in 3D. You'll see that with the normal maps as well when you see an example of the normal map. And as you can see down here, when you apply the displacement map, it essentially determines whether or not a particular vertex is going to move up or down. And that's where the normal map comes in. The normal map can adjust the direction that it goes in. So you can have the normal map like point a little bit to the left, a little bit to the right in any particular direction. And then it'll move along the normal map rather than just up or down. And it gives you a little bit more detail when you're adjusting the mesh with the displacement map. All right, here's an example of the normal map. Again, this is the diffuse map. This is just with the color. And as you can see, once you apply the normal map basically, it kind of fakes the little nooks and crannies that are going to be in there. So as you can see, it's affecting the silhouette. So the lighting here is going to be a little bit more accurate. In areas where it should be dark, it will be dark and stuff like that. Whereas over here, the lighting is still being applied in the same place. You just can't see it at all. All right, now let's look at the code. Again, this is what we're going to be building right here. I'm not going to do a live code demo because this is a lot of code. It's not that much code compared to like what you would normally have to do, but it's a lot to live code. All right, so this is the basic app. So as you can see here, I'm loading in some Google fonts. I have some custom styles here that I'll go into later. I'm loading Three.js here. And I'm loading this file entry.js. And this is my content. This is all the content that I have. And notice that I'm putting the content after I'm putting my scripts. This is important because Three.js, what it does is it injects a canvas into the body. Well, you can put it wherever you want, but I'm injecting it into the body. And the content needed to be rendered on top of that. So I need it to exist after the canvas so that I can use that position absolute to make sure that it's anchored correctly. All right, so let's look at the code real quick. All right, so right here, you can see the initialization. I'm setting up the scene and the camera. The camera is being configured to grab the aspect ratio from the window size, essentially. So I'm just dividing the width by the height. And over here, when I'm defining the renderer, I'm setting the renderer size to the window size. If you're doing something like this, you're going to want to add a hook for window resize, and then you're going to have to recompute the renderer and the camera. And they probably shouldn't be constant if you're going to be doing that. But that is something to be aware of. So yeah, I'm using a WebGL renderer. WebGL is the OpenGL standard. OpenGL is it was the first like GPU API that was programmable. So it allows you to basically like set up a GPU to do some rendering work for you. It does a lot of the hard work for you because it's circuit optimized, so it automatically like threads everything for you. You just need to write the code for one instance of everything, and it'll automatically distribute and run on all the pixels or all the meshes or all the triangles at once, depending on what shader you're running. And WebGL is just an implementation of the OpenGL embedded standard 3.1. So so we set up the camera, the scene, the camera, and the renderer, and then we configure the renderer with some things. I modified the clear color, which is the color that is put in the background. Every time you render, you have to set a clear color, which is it colors in the entire screen a particular color before it starts rendering stuff. It's pretty close to black, so it doesn't really look much different, but you can change that to whatever color you want. And over here, I'm enabling tone mapping. This ACES Filmic tone mapping. Essentially what it does is it does some color correction using the ACES color space. ACES was developed by the Academy. The people who created the Academy Awards, they have a research lab that does computer graphics research for within the context of CG, and they developed this ACES color system to get accurate color when rendering in 3D. So that's something that's supported by Three.js, but you need to have the ACES color system support for your monitors to be able to use it. So if it is available, it will be used, and it's currently being used on my computer because I have support for it. And yeah, it's doing the output encoding in sRGB. So it's outputting the code, the color in sRGB by default, and then it's doing the tone map to create the color for ACEs. Tone mapping is just a post process where you take the colors and you move them into another color space. In this instance, we're moving it into the ACEs color space. And this right here is where I'm injecting the canvas. So the renderer.dom element is an HTML canvas. And for the lighting here, I'm creating a hemisphere light. A hemisphere light is essentially, it's a dome map, which is kind of a weird thing, but essentially it's like simulating a sky, and you can set it to a color. So I set it to this particular color here, and is blending with this color on 2 axes. It's pretty much just this color though. And then yeah, I'm adding it to my scene. Then I created a second light, this ambient light. An ambient light is just a little bit of light that makes everything just a little bit brighter by default. And I'm setting it to this color right here. And then I moved my camera back a little bit by setting the Z position to 5. These are some constants that were defined. So like I said, I'm using a plane to generate the height map. So the width and the height for the plane are stored in these constants here. And this is the displacement value. Remember, the displacement scaling value needs to be multiplied by 2. So I'm actually using a displacement scaling value of 150, but I had to multiply by 2. And these textures right here, these are textures that I'm using. So this is the displacement map right here, this height map, and this diffuse map is the color texture, and this bump map is the detail texture. And this variable right here, the animation start, if you look at it here, when it loads, you see that it starts as a flat plane and then it like starts animating in. That's all that is. This has a timer on it right here. After 1.5 seconds, it's gonna just automatically start animating in. And I needed these global variables to exist because I'm changing their state in another function. So the mesh and the material for the ground plane, where I'm storing the vertex data for the mountain, those needed to be global because I have 2 separate functions here. All right, so I do this set timeout to start the animation, and I have this this initialize texture function. I needed this helper function because it was too much work to type this 3 times. So all it does is it uses a texture loader. So what that'll do is it'll grab the pixel data from a texture and store it into a byte buffer in JavaScript so that you can do a quick lookup. And the texture wrap, this just defines the UV behavior. So the UV texture, the square texture that you can see. So in the top left corner, it's like an XY plane, but we're using the coordinates U and V because X and Y already exist. So the top left would be like 0, 0, and then the bottom right would be 1, 1. But there's nothing stopping you from going outside of that coordinate space. So this wrap behavior defines what happens if you put something outside of that coordinate space. So we're doing a repeat. So what this will do is it'll essentially turn it into a tiling texture. And then we set the repeat value to 1. If we set this to something other than 1, it would essentially divide the U and the V coordinates by this number, essentially causing it to wrap faster or tile more often. And now we're just returning the texture so that we can use it. So here we're creating the ground plane. So they have this plane geometry function in 3JS. You pass in the number of rows and columns you want, and then the size that we have stored in the constants, and then that creates the primitive. And then you use the primitive to source the mesh. So the mesh needs 2 things: a material and a primitive. So we source it with a primitive and then this material. So right here, we're just loading the textures with the code that we already went over. And here we're defining the material that we're then using for the mesh. So in the material here, It's using the mesh standard material, which is their PBR material for physically based rendering. We're not taking full advantage of the physically based rendering, but we needed to use this texture to get access to displacement mapping and the bump mapping. The displacement mapping is available in other texture model and other material models, but the bump mapping was not. The bump mapping is only available in the PBR material. All right, so this map right here, I don't know why they call it that. That's a very weird convention, but that's the primary color texture. So we're passing in the diffuse map, and this displacement map here, we're passing in the displacement texture. And initially we're setting the displacement scale to 0 because we're animating this later, which is why this needed to be a global variable. And then here we're setting the bump map. So this bump map was, it's not necessary given what we're doing, but it does make the model look a little bit better given the fact that the texture doesn't have a whole lot of quality for the diffuse. For the scale we're rendering at, it should be like a 2K texture, but it's actually a 1K because I didn't want to pay for the terrain stuff. And then the bump scale, again, this just defines tiling behavior. So if I wanted my bump map to show like a bunch of fine detail and tile a little bit more, I could make this higher and then it would scale more. If I make it lower, it will scale less and it'll stretch it out, make the detail larger. So here I'm defining the mesh. I'm using the ground plane primitive and I'm passing in that material that was defined. And then I'm adding that to my scene. So when you add stuff to the scene, it's just setting up the render. The scene graph knows how to render stuff. It's kind of like adding stuff to the DOM, but for 3D. So once you add something to the scene, as long as it's set up correctly, it'll just start rendering. And then here, we're setting some initial rotation. So we're just rotating by pi over 3, so you can get we can get the angle that we're looking at. And I'm setting it back to negative 300 in the Z so that it's far back enough so that we can get the view. And then we call this function. This function is not properly named. I'm calling it create and render terrain because initially I was rendering the terrain in here. But then I moved some initialization code in here, so I didn't want to keep calling it in a loop. So I moved the render stuff over here. But yeah, I called that. And this is the initialization for the model stuff that I was mentioning. All the texture and model stuff got initialized there. And this is the render loop that keeps running forever. So when you're doing 3D rendering or any type of fancy animation in JavaScript, you're going to want to use request animation frame. That's going to lock you in at 60 FPS. It's going to force it to basically run at 60 FPS. You won't have to wait for the event loop to render because that can stall sometimes. This kind of guarantees that you're going to get that 60 FPS performance, assuming that the CPU can actually handle it. All right, so here you can see animating the plane mesh, the Z rotation by 0.001 units. I believe this is in radians. So it's rotating by that many radians, and that's why you have the constant rotation that's happening here. And here I just have some basic Boolean logic to make sure that this doesn't start until I get that animation trigger going off. So once that animation trigger goes off, then it's going to start to animate. And I have this ternary statement in here so that it only animates when it absolutely has to. And then once it reaches the max displacement value, it no longer animates because otherwise it would just keep going until it, I don't know if you've ever seen a 3D object scramble, but essentially what happens is if you stretch it out enough, it'll just start turning into like spaghetti. So there's that. And then when you call renderer.render, that just renders everything and you just pass it a scene and a camera and that's it. So then we call this render function and it just, it'll keep going in a loop by itself because we're doing that request animation frame. All right, so that's basically it. Does anyone have questions? I know this was a lot.
No, lightweight, no problem. That was fantastic what he did. That was fantastic. Let you catch your breath, get a sip of water, because I'm sure there are plenty questions. I have an entire book of questions myself, but I definitely want to give space to all of our guests, everybody who came in this evening to ask theirs first. So everyone, now's your time. Anything you want to know more about or get more detail on, just turn on your mic. There's no auto system. We're not going to raise hands. Just turn on your mic and start talking. I think I see a hand raised. Thanks for the politeness. Feel free to turn on your mic and ask your question. Morgan.
Hey there. Okay, so I am very new to the world of code, and I was wondering, because this is a really awesome project that you did here, what type of math logic did you do or did you use?
There, to be honest, there wasn't really any math, which was surprising to me, because usually this involves a lot of math, but JavaScript, this Three.js framework kind of hides it. All the math that I did was basically right here, this and these rotations. It's not like super crazy, but I guess you do need to have that 3D awareness to know like which axis to rotate around and by how many degrees and stuff.
Sweet. One of my friends, she does this type of coding for Roblox, and like listening to you guys and like seeing your projects is just so cool. So thank you for sharing.
Absolutely. Awesome. Roblox, you turned them down, right, Whittington? Am I allowed to say that?
I didn't. They asked me to interview, and then I told them I just didn't want to.
Thought I remember correctly. All good. Next question. I'm sure there's tons. Who else would like to ask something? Whittington, while we have him. While they're thinking of theirs, I definitely have like a ton. So I'm just asking an easy one. In the regular front-end dev space that does not involve this type of animations, I'm thinking of a process and a workflow in terms of design. Design hands their design over to the coders. Does a similar thing happen with 3D rendering? And what is it? Who are the designers? What kind of, how does that work?
Yeah, so this kind of work, typically you would work more with like an interaction designer. So because it involves like motion, so you'd want to work with someone who has a lot of background knowledge in motion graphics, and they're typically going to be generating the 3D content as well. So they're going to be closer to an artist than they are to like a designer. Oh yeah, I forgot to mention, by the way, there's some more code. Basically, I had to write some code to generate some offset. Basically, I had to like create my own like positioning framework to do the position absolute and still have the text centered. So right here, this thing here is completely like position absolute, and I'm just like running some code to like figure out where to center that. That's something that's kind of a pain that you're gonna have to deal with Three.js. You're gonna have to absolute position stuff, and then from there, once you absolute position like one div, and then everything else can be like relative after that. So that's something to be aware of.
When you say absolute position, is it absolute position in a 3D space or just flat like normal?
Like CSS right here. Where is it? Yeah, right here, position absolute.
Yep.
And then yeah, there's the top.
Hi, quick question. So this looks like it's probably doing a whole lot with that HTML canvas. And I wonder if you run into any sort of cross-browser issues with this kind of thing, or if there are any browser-based considerations you would need to make for this kind of project.
Not really. Once once you know you have WebGL support, it'll work. So the WebGL is like a unified standard, and all the canvas is a texture that you write to from the GPU. So once you have support for HTML canvas, there's no like HTML specific things that you're doing from that point. It's all on the GPU.
Right. Okay. Well, that was the other half a question that I had, which was that related to whether or not this was being GPU accelerated or if you were relying on the software. But I think you just answered that.
Yeah, that's the thing about Three.js. It's using the GPU. You could do this. What I'm doing right now, you could very easily do this on the CPU, and it wouldn't be too heavy. But some of the more advanced Three.js stuff, that's like rendering like full games and stuff, you definitely need a GPU for that. But this particular thing, I could use their CPU rendering feature, and it would still function fine without freezing anything.
That's neat. So I guess you don't, I mean, I guess with this, you're getting to rely on the hardware a bit more. You're not running into some of the potential performance pitfalls of doing complicated things in JavaScript.
Yeah, there are some things that would suck to do in Three.js, like animations and stuff. So certain types of animations like Cloud Sim and stuff like that, you can't do on the GPU because they don't support the necessary types of shaders to run that kind of comp on the GPU. So you'd have to do it on the CPU, and with JavaScript, it would be kind of slow. So you could still get bottlenecked on the CPU side if you're trying to do something advanced that pairs CPU computation with GPU computation. With 3D work, you typically don't get bottlenecked on the GPU side. It's usually stuff that's being done on the CPU that can't happen fast enough to feed the GPU.
Neat. Thanks.
All right, do we have any other questions? My next question was, when are you going to replace the battery in that smoke detector? Because I want you safe, man. I actually like you and don't want any issues.
Oh yeah, I had to put in a maintenance request for that. So I have 13-foot ceilings, and the smoke detector is like so high that I can't climb on anything in my apartment to reach it. I need a ladder.
Cool. It's all good. It's a little brevity.
Oh my gosh. I thought that was me for a minute.
You probably saw me. I did the same. I took my headphones off and I looked around. Oh no!
Like I got up and walked around. I was like, which one of these is doing that?
Yep.
I walked all the way through my office and into my living room trying to find out if it was mine.
Okay, I don't feel as bad. So we all did the same. Awesome, awesome. Any more questions for Whittington? About the code, about the project, career? What's going twice? Oh, GitHub down in the chat. Thank you.
Yeah, that's a link to the repo. You're gonna have to do some stuff to get the textures to load first if you want to actually like run this on an actual website. But if you run it locally with like a live server, it should run fine. You cannot run this by just clicking the index.html. You have to run it off of some sort of server because the images need to be served up since they're being pulled from JavaScript. But I haven't done web development in a while, and I wasn't like immediately aware of a way to preload Dash.
Fantastic. Thanks for that link. I'll include it on our Slack when I post the video tomorrow. One last try. Any last questions for Whittington? Well, we thank you for coming out this evening. This was awesome. I think we got a good recording, good video for the community as well as the code. So that was awesome. Let me go ahead and make my standard announcement. So this Friday at 11:30 Central, that's our UI UX meetup. We have one of those every month. Really fun, really interactive, great for people like me who have absolutely zero design inclinations. So be sure to join us there. And then our meetups for August, I think we still have openings for the Coding Dojo. Eric is one of our leaders of the Coding Dojo. That's where we do whiteboard type interview challenges. So if you want to be the driver, but not be just left on your own, you'll have somebody there to kind of help you through, help you when you get stuck. We have an opening for that. Just let us know in the Slack, as well as the featured speaker talk, which will be the fourth Tuesday in August, whenever that is. There's an opening there. So if any of you have a technical topic, you want to take the seat like Whittington did, we'd love to have you. Just let me know. Outside of that, again, thanks to our featured speaker. Follow him on TikTok at _Whittington. He serves the spicy content on an almost daily basis. And thanks again, man. We appreciate you very much. You'll have a great night. Stop.